Okay, a man with blood type A marries a woman with blood type O. Their child has type O blood. So what that tells me is that the man is heterozygous for type A. The woman is heterozygous for type B. So there's a 25% chance, if you do that Punnett square, of making a child with type O blood. And so they can make an AB, they can make a heterozygous for B, they can make a heterozygous for A. So that answers number 5. Number 6, PKU, an inherited disease caused by a recessive allele. If a woman and her husband, who are both carriers, have 3 children, what is the probability that all 3 are normal? Okay, so normal just means not little a, little a. So this is just, this is just a classic heterozygous times heterozygous, giving us a 3-to-1 ratio. So the probability that all are normal are 3/4 times, so child number 1 is normal, and child number 2, and child number 3. So that's going to be 27/64. What about, let's skip to C, all having the disease, so that's 1/4. So child number 1 is 1/4, and number 2 has the disease, and number 3 has the disease, 1/64. What's the probability that at least one child is phenotypically normal, right? So instead of going through all the different permutations of what it would look like to have at least one kid be normal, you can just look at it from this perspective. Well, this is the probability that all of them are sick. So what's the probability that they're not, every single one is sick? That's the same thing as saying that at least one is normal, right? If they're not, if they don't all have the disease, then at least one is normal, right? 1 could be normal, or 2 could be normal, or all of them could be normal. So that just represents, the at least one phenotypically normal child is just 1 minus the probability of having all 3 having the disease. So the probability that they're going to have at least one kid who is phenotypically normal is 63/64. And if that doesn't make sense to you, you're not going to see a question like that on a quiz or even on the AP exam. I'd be shocked. 1 or more of the 3 children have the disease. So that's just looking at scenario A. This is the probability that all of them are the normal phenotype. So the probability of the alternative, which is at least one doesn't have the normal phenotype, which means at least one has the disease, is just 1 minus 27/64. And by 1, I mean 64/64 minus 27/64. So that. And again, I do not think you're ever going to see anything like that on an exam. Definitely A, definitely C, I would expect, or I wouldn't be surprised, but I'd be surprised if you saw B or C, or B or D, B or D. All right, so let's do big A, little a, big B, little b, big C, little c, big D, little d. I'm going to do the math for one of these, because if you understand how to do the math for one of them, you just apply the same logic to all of the other ones, right? You have the key, you have the answers. So I'm just going to go through how to get to A, for example. All right, so I'm just going to do a cross for A, because the crosses for B, C, and D are going to look the same. You're going to have 1 homozygous dominant, you're going to have 2 that are heterozygous, and you're going to have 1 that's homozygous recessive. So the probability of getting a heterozygous genotype is 2/4, and a homozygous recessive for B is 1/4, right? Because that's the probability of getting a homozygous recessive. And a homozygous recessive for C is also 1/4, and a homozygous recessive for D is 1/4, right? So this becomes 2/256. All right, so you run the same sort of logic for B and E, B through E. What is the probability that each of the following parents will produce indicated offspring? Right, so I'm not even going to go over 8, because if you understand how to arrive at the answer for 7A, 8 is the exact same problem. The only thing that's different here is that you just have to make sure you're paying attention to what the genotypes of the parents are, because that's going to determine how you set up your Punnett square. Like for 7, it's easy because or I guess easier, because every parent is heterozygous for every trait. So you can just keep referring back to this Punnett square, right? But for 8, you might have to, if you can't see the Punnett square in your mind's eye, you might have to sketch it out, right? So like, let me pick, I guess, maybe a slightly trickier one. So like this one, if you can't work out the probabilities in your head, you're going to have to do a Punnett square for A, and you say, okay, they're all big A, little a. So the probability of big A, little a is 1 over 1, right? It's 100%. And then you have to figure out, okay, B, okay, they're heterozygous for B. So let me, if you don't have it in your head by now that it's it's a 1 to 2 to 1 genotype ratio, 1 to 2 to 1 genotype ratio. It's a 3 to 1 phenotype, but it's a 1 to 2 to 1 genotype ratio. So big B, little b, okay, 1, 2, so 2 out of 4. So times 2 out of 4 times, okay, this is big C, this is little c. Well, they're all going to be big C, little c, so that's 1. Right, so the probability here is just 2 over 4, or 1/2 for D. Okay, so this is very similar. Number 9 is very similar to what we did with our sickle cell and blood type activity. So here's Steve, here's Karen. They have a sibling. We don't know the sex, so I'm going to do a little diamond that have sickle cell disease. So she has a sibling with sickle cell disease. And basically, their parents didn't have it. So we know that their parents are carriers, right, because these people are affected. And they want to know the probability that they'll have a child with sickle cell disease, right? So for Steve, think back to his parents, right? His parents are big A, little a. So if I do big A, little a, I'm trying to figure out the genotype of Steve, right? So when Steve's parents make a baby, these are the probabilities. But we don't want to say that the probability of Steve being a carrier is 2 over 4. Because by saying that, we're saying that this is a possibility, but it's not. He doesn't have sickle cell disease. So get that out of the list of possible genotypes for Steve. So now the probability that he's a carrier is 2/3. Same for his partner, Karen. The probability that she's a carrier is actually 2/3. It's not 1/2, it's 2/3. But not only do they have to be carriers, they also have to pass down little a. So the probability of Steve being a carrier is 2/3. And passing down the little a is 1/2. The probability of his partner being a carrier is 2/3. And passing down her little a is 1/2. So all of these have to happen. Not only do both of them have to be carriers, but both of them have to also pass down little a. So the total probability is, 4 over 36, or 1 over 9. I think this is like literally one of the exact same problems that we worked through on the sickle cell and blood type. All right, number 10. How do I know whether curl allele is dominant or recessive? Okay. So let's say I have a curl cat. Let's use U for curl. Well, that looks the same. I'll use R. All right, so the cat is curl. And then I have a cat, no curl. All I'm going to do is I'm going to mate a curl cat with a no curl cat to produce the F1 and just see what they look like. Let's assume curl is recessive. Well, if curl is recessive, this is a true breeding cat. And this cat is no curl. If we assume no curl is dominant, this cat could be big A, the cat could be big A, little a. So we have to look at what the F1 looks like. If curl is recessive, then we will either see 50-50, right? We'll see a 50-50 if the no-curl cat is heterozygous, right? Because 50% of the kittens will be big A, little a, 50% of the kittens will be little a, little a. And again, all of these little a, little, all of these curly kittens, I said I was going to use R, but then I went back to using A. They'll be true breeders, right? If the cat is homozygous dominant, then all of the cats are going to show no curl, right? But then if this is the case, I just breed these, and I get my 3-to-1 ratio. And again, like these are my true breeding cats, if curl is recessive. Easy, right? What if curl's dominant? Again, we breed. So if curl is dominant instead of recessive, let's mate it with a no curl. So this no curl would have to be a little a, little a. This curl could start off as a true breeder. And in that case, all the cats would be curl, right? And then to create a true breeder, I would mate it with more curl cats. I would mate the F1 together, and yes, that would be inbreeding. And yes, this is why breeding traits into certain animals often results in other complications, because it does involve a lot of inbreeding. And we would get this, right? We would get 75% of our children would be curly cats, and 25% would be no curl. So if I wanted to create a line of true breeders, I would have to basically take some curly cats with their curly ears from this F2, right? So this is the parental, this is the F1, this is the F2. And I got, 75% of my cats, 75% of my males are curly, 75% of my females are curly. What I would need to do is I would need to take, like, let's say I wanted to create a true breeding male. I would need to take a male, right, male down here, and take a female who is straight ears, non-curly ears, because I know she's little a, little a. Now, I don't know what this male is. He could be big A, big A. He could be big A, little a. In fact, it's more likely he's big A, little a, right, because that represents 2/3 of the dominant phenotype, whereas only 1/3 of the dominant phenotype is going to be true breeding. So what do? I mate them, right? Meow, and they create 100, that's a lot. They create 16 kittens. And 8 of them are curly, and so cute. Choked on my spit. And 8 of them have straight ears. Is this male a true breeder? No. Bye, kitty. Bye, kitty. Right, and so then we pick another male, and we just rinse and repeat. Right, we just keep breeding until we get to a point where they have some kittens, and all the kittens are curly. 16 out of 16 are curly, right? If we get that, then that tells us that our male is a true breeder, and he must be big A, and all these kittens are big A, little a, right? And this male's going to die one day from old age. So if I want to continue the true breeding lineage, I'm going to need to go back over here to my females and do the same thing, right? I need to find a true breeding male and a true breeding female so that I don't have to keep doing these test cross. But if at any point, a true breeder dies, I I just have to go back to the drawing board and rinse and repeat this process, right? And that's assuming that the parent starts out as homozygous, like he starts out as a true breeder, right? But I wouldn't know that. I just know that he has curly ears. If he starts out as heterozygous, then we immediately jump down here and start performing these crosses. We would, I mean, that's basically what we're doing here, right? If we do this cross and the cat starts out as heterozygous, then we'd get a 1-to-1, right? We'd get some half curly and half straight. And then at this point, I would, all of these would be big A, little a. I would cross it with another big A, little a, and then bam, I'd be right back at this scenario, right? So it just involves a lot of crosses and a lot of observing the phenotype of the offspring. That was probably more information than we needed, but that answers number 10. All right, I'm going to stop the video here, and I'll pick it back up in another video just so I don't lose my progress.